Before jumping into particular example, we will see some of the elementary and very important properties so that you can start applying them in the problems. This terminology is very important, so I have written the terminology: homogeneity property, superposition property, and then if you mix them both together, this is called a linearity property. So linearity is not a separate property. Homogeneity together with the superposition is called a linearity property. So of course they are very simple, but at the same time they are very important, and the terminology is very important. So let me therefore write down what do you mean by homogeneity property. So they are nothing but, let me, before starting these properties, where from these properties come from? They are essentially properties which are coming from the integration, because Laplace transform means L, therefore L is an operator. So for example, in quantum mechanics, you know that the operator is represented by the hat there, so it's called L operator. So Laplace transform is an L operator. L operator is nothing but you have an integral operator, so integral is an operator. Differentiation is also another operator. So if you are going to write d by dx is an operator. So operator means something which will operate on a function and that will give you a result. Operator will operate on a function which will give you a result. So d by dx will operate on sin x, it will give cos x. So everything is operator. Therefore, if I say that there is a property for the L operator, where from that property has come? It has come because of this integral. So you already know many properties of the integration, and therefore you can borrow those properties and then put it for the L operator, namely the Laplace transform operator. So in that way, there is nothing much complicated or there is nothing difficult to understand, but at the same time you need to know the names here. Okay, names are very important. What do you mean by homogeneous property or homogeneity property? Is that the Laplace transform of a constant times the original function. The original function is f of t. K is a real constant. This is very important. K has to be real constant. Real and imaginary in the complex, we have to be very careful, because in the case of Laplace transformation you have the S parameter, which is in general complex. So here we are not going to consider about the complex quantity, we are going to consider the real. So in that case, we can say that this is given by the integration k. If you put here, the k will come outside. There is an integral k, if I am going to put, k will come outside. Therefore what happens is, it is k times Laplace transform of the original function. It is that simple, it's very simple. But then why should I explain such a simple thing here? The point is that in exams like GATE exam or CSA or NET examination, you have some multiple choice questions, and if the question will be like this: choose the correct answer, choose the wrong answer, like this questions will be there. And suppose one of the questions says that, or one of the options says that Laplace transform does not satisfy homogeneity property, like that one option is there, then even though this equation looks so simple, you do not know the meaning of the word homogeneity. Because of that reason, you will lose the opportunity to score the marks in the examination. So even though things are looking very simple, you have to be careful with the terminology. So names are very important. Now similarly, superposition means just one upon the other you are adding. So addition actually. So that means if I am going to add, if I am going to have one function of t, and then if I am going to have another function of t, mathematically we say that this is function of t, function of t. Okay, in physics and engineering we say that f1 of t is one signal, one input signal. f2 of t is a second input signal. If I give two signals to my electrical circuit, and the circuit is doing something, and it will give you an output. Okay, so that is how you understand. So f1 of t, f2 of t is one signal here and another signal here, and in mathematics we say that they are functions of t. That's all about it. And we are asking the question, what happens if I am going to take Laplace transform of this combination? The answer happens to be very simple, because the L operator is nothing but the integral operator, and therefore the integral operator, when you have a plus, you put the integration separately. Here separate integral and here separately, which means that you can easily write down that L of f1 of t plus the Laplace transform of the f2 of t. That's also quite simple. This is called the superposition principle. And if you merge them, okay, why should you have two separate properties? Why don't you combine and then write down as a single property? So if you combine them and then write down as a single property, and that is known as the linearity property. What do you mean by how can you combine and put, how can you put like that? Is that that how do you combine this thing is that constant can come here. So I'll say that there is a constant 1 for the function 1, and then, so let me not write here because I am supposed to write here, right? This is linearity. So you'll be writing like this. You are going to put the constant corresponding to this. So I'll be writing k1 f1 of t plus second constant for the second function. If I'm going to add that, then you know how the result will come. There is a result here where k has come outside. Therefore, you have k1 times the Laplace transform of f1 of t plus for that for the second function. So this is the linearity property. So properties, even though they are looking very simple, they are very important. Our conclusion is that the Laplace transform operator, like this Laplace transform operator, is a linear operator. Okay, this terminology is somewhat required for you because in quantum mechanics we deal with linear operators in quantum mechanics. Okay, so in that way this terminology operator is very important, and linearity is very important condition. Otherwise you cannot do many calculations. Okay, linearity is the one that is going to be very important in quantum mechanics. So that way, even though equations are looking very simple, they are going to be very powerful. Okay, keeping these examples, let us move to an example problem wherein we will see how we can use the yesterday's class work in order to get the Laplace transform of some simple functions. So what we have done in the last class, we have this result actually. So this is the result of the previous class, okay, yesterday's class. Laplace transform of e to the power of at is given by 1 divided by s minus a, and where we have considered that a is a complex variable, and already s happens to be a complex parameter, and this entire expression is valid subject to the condition that the real part of the s, okay, subject to the condition that real part of the s will be greater than real part of e. This is the result that we have from the last class, and from here we can quickly calculate the Laplace transform of many of the functions. So that is what we are planning to see today. Now you ask the question. So this is completed. This is yesterday's classwork, and today we are going to ask, okay, based on this, how are you going to calculate the Laplace transform of cos of omega t? So that is how the question comes. We are not going to repeat the integration. Okay, you can always do this. Of course, you can always do this integral 0 to infinity the given function. So put the given function, then multiply by e to the power of minus st, then do the dt here, perform the integration, you get the answer. But we will not do that because there is an alternate way of getting the answer based on the yesterday's calculation. That will be much more convenient and easier rather than performing the integration. Therefore, we will not do the integration now. But instead of doing the integration, we will try to get it from here. Okay, for what you understand is that before doing any calculation, first you understand taking the Laplace transform is okay, that we will do later. First let us understand what is cos omega t. Cos omega t is nothing but, you can see that this is e to the power of I omega t plus e to the power of minus I omega t divided by 2. So that's clear, right? E to the power of I omega t, because that's quite familiar. You just write down the Euler formula. E to the power of I omega t is cos omega t plus I sin omega t. So for this minus, there is a minus will come, then add them. If you add them, plus will be there, minus will be there, this will be cancelled. 2 times cos omega t will come, that 2 I am putting here. So basically this formula you will be knowing. So based on the Euler formula, you can get it from here. Now what is the use of this expression is that cos omega t is nothing but e to the power function. And for the e to the power function, you already have the answer. Therefore, there is no need to perform the integration again. We will use the same function for this. So therefore, what happens is, we are now asking the question, not for cos omega t, but for e to the power I omega t. So we will do the calculation for e to the power of I omega t. So for that, what you have to do, you have to compare these two things. So if you compare these two things, there is a t here, there is a t here. Therefore, a must be equal to I omega. Okay. So this implies that a equal to I omega in equation 1. So where is equation 1? So this is your equation 1. This is important. This condition is very important. So I will not forget about it. So if you are going to use this, you are going to substitute a equal to I omega in this, and remember that a happens to be a complex number according to the yesterday's discussion. So this is not a real. Okay, so directly let us substitute. So in that case, our answer is therefore equal to Laplace transform of e to the power of I omega t will be equal to, this is 1 divided by s minus a, s minus I omega. But that is not the end of the story, comma, this you have to write down, that this equation is valid provided real part of the s is greater than real part of a. Now you ask the question, what is the real part of a? This is a. This is a. So what is real part of a? This means real part of a is 0, because I omega is purely imaginary. So purely imaginary, there is nothing is there, which means that 0 plus I omega. That's the meaning. So real part of a is 0, therefore it is greater than real part of a you can write, but instead of that you write 0 here. That's the meaning. So what you understand, quickly you got the result here without performing any integration. You got the expression for e to the power of I omega t. Similarly, you can also write down immediately for e to the power of minus I omega t, you will be writing 1 divided by, so you compare with this and that, a equal to minus I omega. So if I put that, I will be getting s plus I omega, comma, the condition means ROC, region of convergence, is given by RE of s, again greater than 0. Okay, why 0 comes? Because real part of a is 0, both for this problem and for this problem. So which means that from the yesterday's class, we are now getting 2 more results. Using 2 and 3, you can now calculate the Laplace transform of cos of omega t. Okay, so I will erase this middle expression. So we are having the expression for e to the power of I omega t here, e to the power of minus I omega t here and here. So we can now directly substitute these 2 expressions into that and then divide by 2. So that will give you the answer. So that we can do it here. So 1 by 2 is there. So let me put 1 by 2 here into this plus that. That means these 2 we will add. Condition is a common condition, so we can keep the common condition. So if we are going to add these 2, so it is 1 divided by s minus I omega plus 1 divided by s plus I omega, comma, subject to the condition that real part of s is greater than 0. So since we have written that, now this we can erase so that we can simplify that previous expression. So therefore, so let me write down, of course this is already Laplace transform is taken, so therefore I have to write like that. This is equal to Laplace transform of this, which is equal to that. Okay, so now this equation is clear. Now you see that your yesterday's problem, even though we have done you may be thinking that we have done an easy problem or a very simple problem, but this is very useful in proceeding further and further calculations. Now there is one more point I have to remember. I have explained you the homogeneity property, superposition property, linearity property, whether you are applying here or not. That is the point. You have a 1 by 2 factor. So 1 by 2 factor is coming, right? That is the homogeneity property. So 1 by 2 is constant, it is coming outside. There is a plus here. So Laplace transform for the first function plus Laplace transform of the second function. That's what you have done here. Therefore, you have applied the superposition principle. So both the homogeneity property and superposition properties are used in getting this answer. Okay, so the rest of the thing is simple. You can now simplify by taking the common factor here, which is nothing but 1 by 2, okay, into, let us write like this, plus s minus I omega by this multiplied by this. So I will be getting s square minus I square omega square. Okay, and which can be simplified. So because this is cancelled, you are getting 2s here. So 2s is there, there is a 2 here. So I can write down that this is nothing but s divided by s square. This is plus omega square, subject to the condition real part of s greater than 0. So on the left hand side, what do you have? On the left hand side, you have the Laplace transform of so this is very useful result. So many places will be frequently using. So let us have this. We have the equation number 4. Okay, what we understand is that we have not done any integration, but we are able to do it comfortably, including the region of convergence we have done. We have not used the any Cauchy criterion. Okay, otherwise every time you have to, if you go for integration, you should do the what do you call the modulus test. So all these things can be avoided because this is the easiest way that you can deal with, and you get this expression for cos of omega t. Now what is the advantage? Once you learn this, now you must be in a position to say that you will be in a position to do the calculations for many more functions. Many more functions means, what are the functions you think? Sine of omega t. Sine of omega t is very similar to cos of omega t, right? Instead of writing a plus here, you have to write a minus here. You put a minus here and put additional I here. Suppose if you put a minus here and if you put a I here, that's it. This expression is sine of omega t. So that means change a minus there, put I here, you get the answer. So therefore, you can get the answer. So Laplace transform of the sine of omega t, you can get the answer quickly. Of course, so in principle, if you want to write the answer here, this s will become omega. So rather than leaving it like that, let me therefore write down that this is nothing but omega divided by s square plus a square. This is omega, right? So instead of a square, I will write omega square. So this is another result that you can quickly get. And is it the only thing that you can do, or can you do more like that you think? Okay. So can you do a Laplace transform for many more functions like that you think? And quickly you can get the answer. So what is the answer that you are getting is, you started here, right? And then you think what can be done here by modifying. One modification you can do. Okay, let me erase the other portions which are not required, because this is the result. This result box I will not erase. That result box is there, so I will not erase. So this portion, I will just erase this portion only. And here you may ask the question, what happened to the region of convergence? The calculation proceeds very similar to that, and therefore the same ROC applies there also. So nothing changes. So actually the same ROC you can write down. It is the real part of the s greater than 0 is applicable for this also, because only the plus minus only we have changed in the middle. Okay. Now we are asking the question whether only these two, or can we do more? Answer is we can do more. How we can do more is, you remove the I here. Okay. And you remove the I here. If I do that, what will happen? So is there any expression on the left side if I remove I? Okay, if I was there, then this is cos omega t. If I is removed, this becomes this omega t here. So let me write down omega t. Earlier it was a cos omega t. Now this becomes hyperbolic cos omega t. That's all. So if you remove the I here, this becomes hyperbolic cos omega t, which means that you can now take the Laplace transformation. That means if I am going to do this omega t, if I am going to ask you to calculate this, then you can do the Laplace transform of this. Which means that once again you can use the same function. So there is nothing new. Only thing is I was not there. Now you can apply directly this, where a will be equal to omega. So therefore what happens is, you can now calculate Laplace transform of hyperbolic cosine. If you are able to do that, then you can ask the question, what is wrong with hyperbolic sine? This is hyperbolic sine of omega t is very similar. You have to put a minus here and put I here. That's all. Put a minus and I here, You write down here, that is the expression for hyperbolic sine. Don't read as sine h omega t, cos h omega t. Like that, don't read. You say that hyperbolic cos omega t, hyperbolic sine omega t. So therefore, what you understand is that once you have one small result, okay, this is the main result that you have. Using this, you are able to generate more number of results based on simple property without doing any integration. Okay, so that is first point, and then you start remembering, or once you write, no, it's automatically you will remember. Okay, you are not going to sit down and read and memorize that, not like that. You start doing your calculation on a rough paper, things will enter into your mind. So you have this expression, you have that expression. Of course, if you simplify, the only difference between this hyperbolic cos and this circular cos, what is the difference between these two is, this is hyperbolic cosine, this is circular cosine. These are called circular functions, these are hyperbolic functions. The difference is only a plus here and minus will come. So if you put a minus here, that is the answer for this. Here minus. And similarly, if you put a minus here, that is the answer for this. So what is only that small changes, you get the answer. So that is one thing, we are happy that we are able to get the answers to some of the problems. And even more interestingly, let us see, sometimes, okay, it looks as if a difficult problem, but if you look in this style, you can also solve another example. Let us say that I am going to do cos of, for example, something like 2t plus pi by 3. Take the Laplace transform of. Okay, that is a question. Question is, calculate the Laplace transform of cos of 2t plus pi by 3. Okay. Initially, it will appear as if it is difficult, and in the sense, what do you mean by difficult is, you cannot start doing like this. You start doing integral 0 to infinity, write down this expression, cos of 2t plus pi by 3, then e to the power of minus st. If you start doing this, then you will be in problem, because you may find it difficult how to do the integration. And that's why I told you that whenever you look at the cos function here, you have to use this one and then get this answer. But if you want to do by this method is good, but this method, what is the missing information is pi by 3. You don't have a pi by 3 here, or something, some constant is not there here. Okay, so you cannot directly apply this result. So you have to do a small modification, then you can get the answer. So the question is that how are you going to proceed to get the answer without performing the integration? The idea is to use this function and this function. You remember these two, these are the two functions we can use and then get the answer for this problem. Okay, that's the idea. Now to start doing the problem, we are not interested in getting 2t and pi by 3. What is so special about 2 here? What is so special about pi by 3? You can always change a number, right? I can put a pi by 5 here. I can put some other number like 7 here. Okay, so 2 and pi by 3 is not important for us. Therefore, what we do is we will consider cos of omega t plus phi. Okay, if you do like that, you substitute omega equal to 2. You put phi equal to pi by 3. So like that you can substitute. That will be easier way rather than dealing with numbers. Okay, let us not do it particular number, because particular number is not gaining any importance. So omega is there, phi is there. This is good. Only missing information is phi is not there here. Okay, remember this result. I will erase this. We will use it when you are substituting there. So here what you do is, we are interested to take the Laplace transformation, but before doing any Laplace transformation, first we have to understand the function, then we can apply the Laplace transformation. And you know that cos of omega t plus phi, you can use the cosine expansion, which is nothing but cos omega t cos phi, then minus sin omega t sin phi. So if you use this expression, simple idea, then you can get the solution easily. Why we can get the solution? Let us see. Phi is a constant. Okay, phi is not a variable, right? So some phase factor, which is a number. It's a number. If phi is a number, cos phi is a number. It's a constant. Constant is multiplied by a function. That means homogeneity property. Minus. Plus or minus doesn't matter. Plus and minus are identically treated similar way. Therefore, whenever plus or minus comes here, it is superposition principle. Again, sin phi is a constant. Constant multiplied by function. Homogeneity property. Homogeneity property is mixed with superposition principle, which means that you are going to apply linearity property. So applying the linearity property, and then you already know the Laplace transform for cos omega t and the Laplace transform for sin omega t. You know everything. It's just one line, you can get the answer. But what happens is, if you don't think like that, straight away if you think how to do directly with integration, you'll be stuck up and you will not have an idea of what to do. And that's all about it. Once you have this, now you can apply Laplace transform on both the sides. Therefore, I'll write like this. So the Laplace transform of cos of omega t plus phi would be equal to, cos phi is constant, so I will write down outside. Then you write down Laplace transform of cos omega t like that, and similarly minus sin phi multiplied by Laplace transform of sin omega t. And now you know these two equations just now we have done. So we can now write down that this is nothing but cos phi into, this is s divided by s square plus omega square minus, for this the only difference is s will become omega, like that you can easily remember. Then this is s square plus omega square. Region of convergence you can later write, because both of them have a common region of convergence greater than, real part of s greater than 0, that you can write at the end of the result. And that's all about it. These are all constant, there is nothing to simplify. The only thing is this is common, so we can write down like this: s into cos phi minus omega into sin phi divided by, this is s square plus omega square. On the left side you have, let me write down like this, this is so this is a factor that you are going to get cos of omega t plus phi, okay, like this, and you put a cos here, and then this Laplace transformation you write down here. So ultimately we got this result, and the region of convergence you can write down that real part of the s greater than 0. And now what you can do is, now I can substitute whatever number you like. For example, you can substitute phi equal to pi by 3 and omega is equal to 2. You put those numerical values and then you can simplify with numbers. Okay, so usually what happens is, in the questions like GATE exam or CSIR exam, when you have numbers like this, okay, you have to put exact numbers and then some values, root 3 by 2, something like that will come, and that result will be given as one of the 4 options. So you should have an idea of how to proceed. So I am just giving the idea of how to approach to start solving a particular problem, rather than always starting with the defining integral. So this is the first idea that I would like to give an example. And similarly, we can do more examples if you are having some more properties. Okay, so you must now ask the question, how we are able to do these problems. The answer is because of the initial one starting point here. So that is one thing. And similarly, and then we have properties called a linearity property. So which means that if you are going to have some more properties, okay, if you are having some more properties, you can solve even more number of problems. So there you understand why the properties of the Laplace transforms are very important. Okay, mathematicians call the properties as theorems. Okay, theorems on Laplace transformation: shifting theorem, scaling theorem, T shifting, S shifting, okay, differentiation of Laplace transforms, integration of Laplace transform, convolution theorem, and so on. The point is that we are not going to worry or don't get afraid of the word theorem here. Rather, we say they are properties. Okay, so once you understand shifting property, scaling property, convolution property, we can solve more number of problems. So that is the overall idea about the class. And in fact, I would like to actually, I was interested to start with the example wherein the Laplace transformation cannot be obtained. Okay, that is how the objective that I was having, but that I will do in another class. Maybe in the tomorrow's class I will start doing an example wherein we are going to show that we cannot find the Laplace transform for the given function. So that is the next idea that we will do in the tomorrow's class. Goodbye.